The term cylinder has a specific meaning in everyday use. When we use the word cylinder when it's related to three-dimensional surfaces, it has a specific meaning. Given a curve C in the plane and a line L that's not in the plane, a cylinder is the surface that consists of all the lines parallel to the line L that pass through the curve C. So take all lines parallel to L that go through the curve C, and that graph will be a cylinder. Now, a specific case that we'll use more often is when the line L is actually parallel to one of the coordinate axes. So in this first graph, we have the line L that's parallel to the z-axis. When you look at the equation of a cylinder, this surface, in that form, where the line L is parallel to one of the axes, then the cylinder itself will be parallel to that axis, and you can tell the equation because that variable will be missing from the equation. So this particular graph in the xy plane is the equation y equal to x squared. Now, if we view this as an equation in, with three variables, a three-dimensional surface, then the z, since it's not specified, can take on any possible value. So what you get for the graph then of that surface would be that parabola y equal to x squared, but now take all possible lines parallel to the z-axis passing through that parabola, and that gives you this surface that's in the graph. Okay, so just look at the parabola and then take all the lines parallel to the z-axis. In the second graph, we actually have the parabola. This would be a parabola in the yz plane. The graph equation would be y equal to z squared. But now take all lines parallel to the x-axis, passing through that curve, and the result is the cylinder that you see in this picture. So that cylinder is parallel to the x-axis here, and it's all the lines then passing through the curve y equals z squared parallel to the x-axis. So that's a cylinder that's parallel to the x-axis. So now to recognize that, look for one of the variables being missing. The missing variable can have any possible value. So graph it in the plane consisting of the other two variables, and then let the missing variable assume every possible value. So now to help us to be able to visualize what these graphs of the surfaces look like, we'll introduce the idea of a trace. A trace of a surface is the set of all the points at which the surface intersects a plane that's parallel to one of the coordinate planes. So for instance, in this first picture, we've got this paraboloid. The trace is that circle or ellipse where the paraboloid intersects with the xy plane. That's called the xy trace if we're intersecting the plane, the xy plane, with the surface. So the xy trace is where this paraboloid intersects the xy plane. So it results in that red circle there. If you looked at another trace of a plane parallel to the xy plane, so let's say we looked at the plane z equal to 4, then somewhere up here we would have a circle where that paraboloid intersects the plane z equal to 4. So that would be a trace with the z equal 4 plane. So in the second graph here, we're intersecting the paraboloid with the YZ plane. The YZ trace would be this graph. So it's that parabola. looking at those traces allow us to see what this three-dimensional surface would look like. So if we know that the XY traces or any planes parallel to the XY plane result in a circle or an ellipse, then we have an idea, you know, horizontally what those traces look like, give us an image of that surface, or with the YZ plane, or in this third one is the XZ trace. So we're actually intersecting this paraboloid with the XZ plane, and we get another parabola. So we know the trace with the XZ plane is a parabola, the trace with the YZ plane is a parabola, but the trace with the XY plane or planes parallel or circles or ellipses, then we can visualize that we have this paraboloid. So the traces are just all the points where the surface is intersecting a plane parallel to one of the coordinate planes. And so XY trace is specifically with the XY plane, the XZ is with the XZ plane, and the YZ trace would be specifically the surface with the intersected with the YZ plane. So now let's sketch the graphs of these cylinders. Now I recognize the cylinder by the missing variable. X squared plus 4y squared equal to 16 tells me that this is a surface that, or a cylinder that's going to be parallel to the z-axis because the z is missing. So you have a cylinder parallel to one of the coordinate axes if one of the variables is missing. Now to see what this graph is going to look like, what does this equation look like in the xy plane? Well, if we weren't dealing with 3 dimensions and we just were looking in the xy plane, I would recognize this as an ellipse, and the standard form is x squared over 16 plus y squared over 4 equal to 1. Remember that standard form for an ellipse, x squared over a squared plus y squared over b squared equal to 1. Okay. The larger of the two on the bottom gives you the square of the length of the major axis, and the other one is the square of the length of the minor axis. So here, since the 16 is the larger one, I know that the a squared is the 16. The a is always the larger, and the b squared is the 4. So the half the length of the major axis is 4, and half the length of the minor axis is just 2. So if I were graphing this ellipse in just the xy plane, I would go 4 each direction. Now since it's x squared, y squared, and there's no other x and y terms, I know it has center at the origin. And then the minor axis has length 4, which half of that is 2. So that's the graph of the ellipse in the xy plane. So now if we were looking at the trace, so there's our x, y, and z axes. In the xy plane, we know it's coming out 4 down the x-axis and 2 up the y-axis. So we have a graph like that, but now that's the curve that defines the cylinder. Now take all possible lines parallel to z passing through those. Now another way to do that is to look at another trace. Let's put another one up here in a plane that's parallel to the xy plane. And now if we actually just connect those, we can see that we have a cylinder that looks something like that. Okay, now this is called an elliptic cylinder. So draw one in the xy plane, draw a second one parallel to the xy plane, and then just draw the lines parallel, which are those lines that actually define the cylinder. Okay, the next one. Notice in this second equation that the variable y is missing, so this cylinder is parallel to the y-axis. And if we want to know what the graph looks like, graph it in the xz plane. So the graph would be x equals sine of z. So If you think about the graph y equals sine of x, that means that z is our independent variable and x is the dependent variable. So the graph would look something like this if we were graphing just in an xz plane. Putting it in 3 dimensions though, okay, it's going to be rotating around the z-axis. And now take all lines passing through the curve parallel to the y-axis. So that would be going this way. So if you want to look at another one down the y-axis and then just connect those, it's going to look something like that. Now I've got a better graph on this next slide. You can see we drew the trace, the XY trace, drew another one in a plane parallel, so just a little bit raised, connect those lines to get that elliptical cylinder. The second one here, we've got our x equals sine of z graph that's in the xz plane. Draw another one just down the y-axis and then connect those with lines parallel to the y-axis, and that gives you the graph. So here's our surfaces defined by those equations.